Okay, it's recording. I apologize. So I left out the introduction from the recording. Unfortunately, the audience heard it. To people in this field, Jim Smith and Lynn Baeck need no introduction. But anyway, please go ahead. Sorry about that.
Thanks, Andy. So the Mid-Atlantic region is not that strange a place to think about the question of how hard it can rain. Not just the US record, but the world record rainfall at 1 minute time scale, 31 millimeters, occurred in Unionville, Maryland, about 30 kilometers northwest of Ellicott City. 31.2 millimeters in 1 minute translates to a rain rate of 1,870 millimeters per hour. It's sort of an unimaginable rain rate. And it's not the only truly extreme historical rain event. A storm that devastated Baltimore in 1903, devastated Baltimore both from flooding and from a tornado. It resulted in the largest rain rates in Baltimore City at time intervals ranging from 5 minutes up through an hour. Now, the Unionville storm probably wasn't all that totally dissimilar from the Baltimore storm of 1903. It was part of a severe weather outbreak on the 4th of July in 1956. There were tornadoes across the Potomac. And so one of the issues that we're going to look at on the extreme end of rainfall is what's the environment of these storms? And convective intensity is going to be one of the big elements that we'll be focusing on. And in fact, a hypothesis is that the most intense convective storms are going to really determine the upper tail of rain rates through most of the United States and certainly in the Mid-Atlantic. So how does it rain hard is going to be a central part of how we examine cloudbursts of the Mid-Atlantic. There's a paired question that I'll touch on really only briefly today, and that is how extreme rainfall varies over the Mid-Atlantic. And the question is whether there are hotspots of extreme rain. Another way of thinking about that is what are the physical mechanisms that are associated with spatial heterogeneities of extreme rain. And then the piece that Andy's going to focus on more closely is this question of whether we're actually seeing changes in extreme rainfall and urban flooding associated with climate change. And I'll pair the last two. One of the issues with spatial heterogeneities of extreme rainfall is it turns out it's large relative to the types of time changes that we're worried about in terms of climate change. So each of these questions is going to play an important role in the types of analyses that we look at. As Andy noted, grounding a lot of this work are analyses that are based on weather radar observations. In particular, Mary Lynn has spent an enormous amount of time working on a high resolution, long radar rainfall data set. So long is now 21 years, covering the period March through September for the years 2000 through 2020 now. Very high spatial resolution, 1 kilometer. The total area covered, which is shown in the image below, is 14,000 square kilometers. And the time resolution for the measurements is 15 minutes. Now, paired with that, Mary Lynn has extracted basin average rain rate for drainage basins. Many of these are USGS stream gauging stations so that we can pair analyses of stream flow measurements with representations of the basin average rainfall rate. And Andy's going to be talking more about those. So this 21-year data set gives us at least a beginning of looking at climatologies, and I'll take a quick look at this issue of spatial heterogeneity of rainfall. These are just two analyses looking at spatial heterogeneity of extreme rainfall, kind of centered around Baltimore, and there are two different types of analyses. The one on the right is looking at the largest 50 storms in Baltimore City, and the city outline is shown in gray. And the odd thing here is that when you look at the largest rainfall in Baltimore City, and you look at the mean rainfall over the region, the maxima isn't even in Baltimore. It is northeast or downwind in many settings. And so that downwind, that northeast maximum in rainfall shows up in a number of analyses. And on the left, it's showing 15-minute periods with 15-minute rain rates greater than 50 millimeters per hour. And again, this northeast maximum associated with both the urban region of Baltimore, but also with Chesapeake Bay. So there are large gradients in extreme rainfall frequency. These are not represented in typical ways of characterizing rainfall frequency like the NOAA precipitation frequency atlases. There just simply aren't the rain gauges to be able to characterize that. There are only a handful of rain gauges that cover the domain that's shown here. And so you're certainly not going to be able to resolve these types of spatial heterogeneities. We've carried out studies using regional climate model experiments to look at physical mechanisms. And kind of the large story here is that it's the interaction of the urban heat island circulation with the bay breeze circulation that really dictates this maximum northeast of the city and on the western margin of Chesapeake Bay. And then the other piece of that comes into play is the Blue Ridge and the impacts that it plays on convective evolution over the course of the day. So our long duration, high resolution rainfall data set gives us a way of looking at this aspect of extreme rainfall, which is certainly one of the most, one of the important elements. But with that, I'd like to turn to cloudbursts rainfall, and the quintessential example is the second Ellicott City storm, the May 27th, 2018 storm. The figure on the upper left shows the storm total rainfall for the event. The red contours are rainfall accumulations greater than 200 millimeters. Tiber Run is the principal tributary river that drains Ellicott City. It has a drainage area of a little under 10 square kilometers. Dead Run has a drainage area of a little over 14 square kilometers. So it was the area from Ellicott City extending over into Catonsville that had the most extreme rainfall. The figures on the right show basin average rainfall time series for the three principal tributaries of Tiber Run. Hudson Branch in the north, Tiber Branch is the smallest central tributary, and New Cut is in the south. It's really New Cut that is the most extreme flood peak of the three. Tiber Branch also quite extreme. You can see that the rainfall distribution shows large spatial heterogeneities with New Cut and Tiber Branch seeing the heaviest rainfall. I'd also point out that looking at New Cut, the heaviest rainfall is in this period from 20 to 21 UTC, and it's really the time period from 2015 to 2030, that 15-minute time period that has the largest rainfall, and that's really what's driving the peak in New Cut Branch. There are a series of storm elements that pass over Ellicott City and to the east to Catonsville. And this sequence of storm elements are what produce 3-hour rainfall accumulations that exceed 1,000-year return interval from the NOAA frequency atlas for more than 100 square kilometers. This is really the most extreme event in the record for the mid-Atlantic. Now, the bottom figure shows cloud-to-ground lightning. This is the second largest cloud-ground lightning flash density in our cloudburst storms, approaching 10 strikes per square kilometer, right over Catonsville. Now, there's a little bit of a mismatch in the lightning and the rainfall over Ellicott City. The convective intensity is largest over Catonsville and less over Ellicott City. So this aspect of how convective intensity plays into extreme rainfall is one we'll look at in more detail. So we've collected a large number of events as cloudburst contenders. These are 10 that we've been looking at quite closely. Most have rainfall accumulations at 15 to 180 minute time interval that approach or exceed 1,000 millimeter return interval. Some of these have produced envelope curve flood peaks like the Ellicott City floods, including the 2016, the May 15, 16, 2018 storm that produced extreme flooding in Little Catoctin Creek, and then the August 2018 storm that produced extreme flooding in Harford County. So there are a collection of these events that we're focusing on and comparing to the May 2018 storm. The figure on the right shows one of the cloudbursts, the July 17, 2017. It has rainfall accumulations at 1 hour time interval that exceed 1,000-year return interval. You can see the bullseye of rainfall right up next to Upper Gwynns Falls. It just missed a bullseye on the Upper Gwynns Falls watershed. It still produced a very large peak in Upper Gwynns Falls. The bottom right figure shows intercomparisons between rain gauge and radar observations. The blue cross very close to the bullseye is the location of this BC 38 rain gauge. And so a separate part of the analysis that graduate student Molly Cheney is focusing on is assessing how well these polarimetric rainfall measurements can be used to represent, to measure extreme rainfall, to measure cloudburst rainfall. So this collection of storms, we look at it from the perspective of the convective elements that produce the most extreme rainfall at whatever the time scale is, 15 to 180 minutes, and localizing to the particular area that receives the most extreme rainfall. So from that point, we then look at what are the convective cells doing, what's the structure, motion, and evolution. How are convective cells organized? They were really organized in a particular fashion on May 27th of 2018. And then finally, what's the environment that's associated with this behavior of storm elements? So we piece these together and assess what the central properties are for cloudburst rainfall. Now, going back to Unionville and the most extreme rain rates, this is an ideal model of representation of a convective cell. It's actually the Big Thompson cloud from July 1976, Big Thompson flood. So we have updrafts, we have downdrafts, we have vertical structure in which we have water that is liquid water that's ice and water that's mixed phase, depending on the temperature. So updrafts, downdrafts, and horizontal winds all come into play in important ways. For cloudburst rain, one of the most important elements is we just need lots of water. Really strong, large updrafts. But for extreme rainfall, the paired side is we have to have really strong downdrafts. That's where the extreme rainfall is located. And the horizontal winds are needed both to transport water vapor into the storm and to move the water in liquid mixed phase and ice phase around so that we maximize the rainfall at the surface. So these elements come into play. They come into play for the May 27th, 2000 Ellicott City storm in a fairly conventional way, in ways that we've used radar measurements to examine in more detail. And in particular, it's the polarimetric radar measurements. And let's just take a quick look at that. This is a look at the Ellicott City storm at 4:17 p.m. local time. So this is sort of the beginning of the heaviest rainfall over Ellicott City. There are three types of measurements made by a polarimetric radar that are relevant here. Reflectivity is the standard one that you've seen. Differential reflectivity is really just a measure of drop size. And then differential phase shift is this odd measurement that's really, you can think of it as almost linearly related to liquid water content. And what we've done is we've adopted methods from the tornado literature to look at characterizing storm kinematics based on polarimetric measurements. And so what we see at 4:17 on May 27th is that we have this tremendous updraft. And associated with it and paired with it is an exceptionally strong downdraft that shows up in the differential phase. So these are the features that show up well above the ground. So this is 5 kilometers in the upper part of the figure here. And this is really what's generating the extreme rainfall. Now, near the surface, we've got heavy rain, as is indicated by the rainfall measurements, but it's not the rain that is associated with catastrophic flooding. The water that is going to produce the catastrophic flooding at 4:17 is in this stretch from 7 to 3 kilometers above ground level. 15 minutes later, we have the cloudburst rainfall at the ground. So at upper levels, we've got a weakening updraft, we've got a weakening downdraft, but we've produced this tremendous pulse of water, processing water vapor, creating this tremendously strong updraft, and then turning it to extreme rainfall at the surface in a downdraft. Now, an odd feature is it's sort of oriented along this east-west orientation that you saw that was part of the rainfall distribution from the Ellicott City storm. So that's kind of an important piece of the rainfall distribution, is that we've got this elongated maxima and cloudburst rainfall. So these are elements that play out in various ways throughout the cloudburst storms that we've looked at. And so thinking about the convective cell as the building block, the way you do the most with a convective cell is have tremendous updrafts, move the water away from the updraft into a region where you can have strong downdrafts, taking all that condensate and getting it down to the ground effectively. So that's the recipe for Unionville, Maryland type storms. Now, one of the features I noted in thinking both about this how hard it can rain and this distribution you see here, and then the sort of larger organization into extreme rainfall over not just a 15-minute time period, but 15 to 3-hour time period, is storm environment. And I just want to highlight a couple of the elements of the storm environment that are really critical here. The figure on the left is from Doppler velocity measurements. It's showing from 19 to 20 UTC, the vertical profile of the horizontal wind. The wind barbs show direction and magnitude. It extends from the surface up to above the troposphere, more than 12 kilometers above ground level. Now, the main features there, we've got the winds above about 3 kilometers are out of the west. They're not particularly strong, but they're west to east, and that's consistent with both the orientation of that region of extreme rainfall from at 4:31 UTC, but also with the way storms are going to move. They're going to be steered by this west to east wind. There's strengthening low-level winds, and those low-level winds are bringing tremendous amounts of moisture. On the right, I've shown analyses at 850 hectopascals, about 1.5 kilometers above the ground. The color is humidity, it's specific humidity. The darkest green colors are specific humidities of about 15 grams per kilogram. Those are large values at 850 millibars. The key feature here in the bottom is this convergence zone. You can see to the south of it, you've got winds blowing south to north. North of it, you've got winds that are blowing in an east-west direction. And so it's storms forming along that convergence zone repeatedly, including the Ellicott City storms that we were looking at that are a central part of the storm environment. So we've got large amounts of humidity. We get up to 50 millimeters of precipitable water. That's a nice big value. We've got steering winds that are west to east. We've got winds varying with elevation, and that's needed for convective intensity. I didn't show you instability, but we've got a lot of juice in the environment for convective. And then this surface convergence zone is really what dictates many of the elements of the rainfall distribution over the 3-hour time period. So these are the kinds of things that I think about when we look at storm environment. We're looking at humidity, we're looking at winds from the perspective of both transport, organization of convection, and how storm elements are going to move. Those are really the key elements that come into play. Taking a larger view, this is showing a regional look at reflectivity, low-level reflectivity. I've identified Ellicott City at 20 UTC. This is leading up to the period of peak rainfall, and you can see rainfall organizing along this convergence zone, convective elements forming lines that are made up of multiple updraft and downdraft. So this is the mode of organization that plays out for the Ellicott City storm and for some of the other storms that we've been looking at. Now, one of the thorny questions is, if you're going to make the case that you understand how these systems behave, you're going to need to demonstrate a predictive understanding. And so we've carried out numerical experiments using, this is the weather research and forecasting model. It's used both for operational forecasting and for regional climate modeling. And the upshot of it is it captures this organization from 21 to 22 UTC of convective organization along this east-west oriented frontal zone. Now, a lot of the details are not captured. They're not captured to the point that you can make accurate forecasts of locations of extreme rainfall. But we can look at some of the features of the storm evolution and demonstrate that we understand some of the key elements. Now, we've carried out numerical experiments where we eliminate the urban land cover, and urban land cover actually plays a significant role in evolution of the storm, largely in dictating the details of convergence and putting it west of the city. So these are the types of problems that we're wrestling with, ultimately looking to show that we have a predictive understanding. Now, we've stepped through similar analyses for these 10 storms, and I'll just point to some broad conclusions. There's a wide range of convective intensity. We have 2 Ellicott City storms that are on opposite ends of the convective intensity spectrum. We have some storms like the July 29, 2017 that don't have any lightning at all, very weak convection, but extreme rainfall at 15-minute to 180-minute time period. Structure, motion, and evolution differ widely among the storms. There's really not a one-size-fits-all representation. There are a number of interesting stories, but not stories that point to one dominant mechanism. Certainly for multiple events, urban heat island, Bay Breeze, and the Blue Ridge play a role in storm evolution. And looking at climate change, we would like to think that water vapor and sort of Clausius-Clapeyron thinking would take us a long way down the road to understanding why rainfall extremes may be increasing. Not a clear story there. Most of these have ample moisture. Some, like the July 17th, 2017, have very modest precipitable water, 40 millimeters. And so there's not there's not a unique story there. There's an interesting climate variability story in 2018. There are 3 here in addition to the May 27th storm, and there are a number of other cloudburst contenders in 2018. So interesting aspects of looking at climate variability and the climate processes that were in play in 2018. Those are also issues we're wrestling with. So I have more questions than answers. One is, are all of these unique, and we're kind of fighting that impulse. We still think that it's the most intense convection that's really driving the upper tail. There are aspects of storm environment that are atmospheric water balance and aspects associated with the wind field and surface convergence that are clearly key players. Are there too many cloudbursts? Do we expect so many 1,000-year return interval events over a region? And how will these environmental variables change in a warming climate? Can we kind of readily alter just little pieces of the May 27th, 2018 storm to come up with a Unionville 31 millimeter rainfall accumulation in 1 minute? The polarimetric measurements provide the path to these types of analyses of extreme rainfall at high temporal and spatial resolution. And finally, Jeff Halverson has been covering these, and I follow Jeff's posts all the time, and he points to the tremendous challenges of forecasting extreme rainfall for these types of events. So this predictability question is really an important one. And with that, I'll turn it over to Andy for more of the rainfall, floods, and climate change story.
Thanks, Jim. Can everybody hear me? At least those of you I can see. Okay, fine. So Jim, you need to stop sharing screen, and then I'm going to share my screen. Okay, share screen. My mouse, here we go. Okay. Okay, can you see that? So we titled this talk, "What can floods in Baltimore-area urban watersheds tell us about climate change?" And this is a picture that was taken in Baltimore City at the intersection of Hill Road near Lake Montebello over near Oregon State University. And that is indeed a bus up to its windows in rain. This is a storm that happened on the afternoon of July 22nd this summer. And the most extraordinary thing about this is that it's not that extraordinary in terms of how we look at these things. So there are 2 local watersheds nearby. One is Moore's Run in Radicke Avenue. Another one is White Marsh Run near Fullerton. And this storm you're looking at here is the first of the 2 that are shown that happened a couple of days apart that week. It's the smaller of the 2, actually. The second one, so these are small urban watersheds. This one's about, Moore's Run about 3.5 square miles. White Marsh Run near Fullerton, less than 3 square miles. And we have between 2,000 and 3,000 cubic feet per second for these peaks, which were generated by a very short duration rainfall. Most of this rain fell in 30 to 40, maybe 50 minutes, and it was no more than a couple of inches of rain. And yet it generates very large flood peaks that come up very quickly, recede very quickly. And it got into the news, but in fact, these things happen around here quite often. Now, this is actually a slide that I got from Jim based on the extraction of the rainfall that went along with the runoff over Moore's Run. The red is the rain rate, and you get rain rates up to close to 80 millimeters per hour, which is very high. But again, for very short duration. That's kind of been typical of a lot of the kinds of floods that we see, urban floods we see in this local area. And you can see that the stream flow responds almost like, these small watersheds act almost like rain gauges. The response looks almost exactly like the rain. So just some background. The Baltimore metropolitan area, I think this sort of follows along with what Jim was saying. Some of the highest frequencies of extreme rainfall and flooding that we've seen in the eastern US. Some of which is a function of the hydrometeorology of the local environment. Some of it's due to the nature of urban development. The rainfall may have some impact, but certainly the flooding is heavily impacted by urbanization. And some of our watersheds are extremely efficient at translating these intense convective precipitation events Jim was talking about into a runoff response. Almost all the large flood peaks fall into the categories that Jim was describing in his talk. There are some from tropical storms as well. And a lot of these are these relatively frequent short duration floods, like I just showed you, caused by normal summer convective storms. But then you get those extraordinary events, the cloudbursts that Jim was talking about, such as the Ellicott City and some of the other events. Now, there is a flash flood hazard. I don't think there have been any fatalities since these, but this is back in November of 2003. There was one of these short duration thunderstorms, came up very quickly in the middle of the afternoon. And actually, there were people who drowned as a result of that storm on the east side of the city and to the west of the city. So flash floods are a hazard. Mostly people manage to avoid them, but there have occasionally been fatalities in the past. So what's causing all of this? Let's just do a little bit of urban hydrology and just point out that we've known about these phenomena for many years. This is a little excerpt from a well-known USGS circular. It was published in 1968 by Lynn Leopold, who was chief hydrologist of the survey at that time. And he described impervious cover and the density of the storm drain network as key controls on urban runoff. And the consequence was this is a version of this figure gets reprinted in almost every textbook that treats these issues. You basically go from what the hydrograph originally looked like to much higher peak, shorter response time, and more of the rainfall becoming runoff as a result of urbanization and also the efficiency of the storm drain network. And an example of this is illustrated by Watts Branch, a study from 2002 that was done by Glenn Moglen and Egg Bailey, showing from 1951 to 1997 the increase in urban cover. Watts Branch used to be sort of rural. It is in fact centered in Rockville. This shows you the land cover trends. It went from only about 10% urban to, I can't see the right side of that slide, but basically up close to 60% urban by the end of that time period. What was the result? Well, I actually went back and looked at data. This is quite a long time ago. The gauge was discontinued in 1987. But for an almost 3-inch rainfall in August of 1959, you got this kind of a hydrograph. Then by 1985, you got this kind of a hydrograph. Half the rainfall and about 3 times the response. Just to compare with an urban watershed in Baltimore, less than an inch of rain in Moore's Run in May of 2000 generated very short duration hydrograph, very, very large peak. And that's actually not an unusual peak for Moore's Run. And you can see the change in the comparison between rainfall and total storm runoff from the period of the 50s and early 60s to the period of the mid 80s. So that we've known about for many decades. And the consequences of this cause all kinds of problems in urban stream channels. This is just a selection of some classic papers, including one that Lynn Leopold published in 1973. And we all know about urban stream syndrome. That actually was published in 2005, but the earliest papers talking about these phenomena go back to the early 70s. So when we talk about these urban floods, the prevailing belief until recently, for which there's a lot of evidence, has been that these increasing trends in runoff and flood frequency that we see in these urban watersheds are almost always attributable to changes in land cover and land use. And this is an excerpt from a paper by Gabriele Villarini, who at the time was a postdoc working with Jim and colleagues at Princeton. And this figure here shows you the increase in the predicted value of the 100-year peak between 1965 or so and about 2008. And it goes from a little more than 7 cubic meters per second per square kilometer up to about 15.5. So you have a more than doubling over that time period in the magnitude of what's thought to be the 100-year flood. At the same time, what was thought to be the 100-year flood in 1965, this is recurrence interval on this axis for the gray line. By 2008, what was the 100-year flood is now more like the 20-year flood. It's happening more often. Now, the question is, what's causing this? Well, population increase in Mecklenburg County, this is in North Carolina, shows dramatic amount of urban development. That clearly plays a role. Does climate play a role? They did an analysis of rainfall And essentially the takeaway message from this is that there's not a strong climate signal in here. Climate might be playing some role, but the change in the rainfall is not at all commensurate with what you're seeing in the terms of change of the hydrology of the watershed. So the question is, that was true. Is it still true now? Or are we seeing something different starting to happen? So this is an important paper that was published in 2008 called Stationarity is Dead with or Water Management. And essentially, it posited that climate change is rapidly altering our predominant assumptions about whether we can use the past to predict the future, whether we can use the time series of floods or rainfall to assess what our future risks are, because in fact, the rules seem to be changing for reasons that have to do with the way the atmosphere responds to what's going on with the global climate. Jim referred to Atlas 14. This is Atlas 14. You can go to the website, you can click on any point, you get a table of values for the rain accumulation or the rain rate for each duration by recurrence interval. And you can then generate what we call intensity, duration, frequency curves. This is based on relatively sparse set of rain gauges, as Jim said. And there's a lot of interest now because of the concern about climate change. It's widely being assumed that these probabilities are changing. And so there's a lot of interest right now in updating the intensity, duration, frequency curves you can get out of Atlas 14. And I'll say a little bit about the HydroNexRad data set in a moment. One way to think about these changes that's kind of interesting. I was involved in this report back in 2008 for the Maryland Climate Change Commission called Global Warming in the Free State. And one of the ways of thinking about it was to say, well, if Chesapeake Bay is up here now, and you think about transposing its location to a location farther south as temperature goes up, then the prediction was by 2050, it could be down here under one set of climate scenarios, under that down here in North Carolina under another set, and that the intermediate set said by 2100, Chesapeake Bay's climate would look sort of like South Carolina, and under a more extreme case, it would look like Florida. So I tried a little game for a talk I was asked to give at a conference on the future of climate in Maryland, which was just to go to Atlas 14, pick Baltimore's 60-minute rain rate for different recurrence intervals, and plot the same thing for Hilton Head, South Carolina, assuming that Baltimore might look like South Carolina. And I wrote here, don't try this at home. This is really just kind of a little game to play. But the point is, if you do make that transposition, then you'd find that what was the 100-year rainfall would increase pretty dramatically. And also that same 100-year rainfall in Baltimore, if it were to look like South Carolina, would be something like the 10-year rainfall. So the question is, what are we seeing happening now? Are we seeing the beginnings of this? Because the assumption up until pretty recently was that you're not really seeing a climate signal when you look at these urban watersheds. You're really looking at the signal of the urbanization. So this is a paper that describes the first 10 years of the data that Jim was talking about. This is actually some of our urban watersheds superimposed on a panel here with the satellite image in the background, showing you, the domain of the HydroNexRad radar data. And we're using these data together with streamflow data, as Jim was describing, to try to parse out what we think might be going on. So we're trying to ask questions both about the spatial and temporal pattern of the rainfall throughout that area, basically treating these 14,000 1 square kilometer grid cells as 14,000 individual rain gauges to carry out frequency analyses for different kinds of rainfall durations. And some of the questions we're asking are we seeing increases in the frequency of intense precipitation over the study domain during the last 21 years? How do these relationships of intensity, duration, and frequency compare with the trends that you can see in Atlas 14? Are there spatial patterns in these relationships by comparison with the relative lack of spatial pattern in Atlas 14? You've already seen some indication that that's the case. Can we quantify changes in the probability of extreme rainfall over that 21-year record? And how do those results relate to projected future changes in the magnitude and frequency of intense rainfall? People are using global climate models to try to predict those changes, but those models don't resolve the very high intensity, very fine spatial patterns that we're looking at here. So we're hoping to be able to give a little bit better baseline for thinking about how what we're seeing now might relate to what people think will happen in the future. Now, I'm not going to show you results from this because we're still working on it, but I'm going to show you some of the local watershed results in a moment. First, I need to give you some background. So the flashiest watersheds in the contiguous United States, as published in a paper by Grant Smith, who at the time was a PhD student working with Jim, include watersheds in Tulsa, Baltimore, and St. Louis. But of the top 10, 2 of the top 10 were actually located here in Baltimore. Number 5 was Moore's Run. You've already seen that. Number 9 was a West Branch Herring Run over here. You see Tiber Branch and Dead Run here. You're going to see White Marsh Run over here in a minute. We typically get these very high bursts of rainfall, and this is kind of response is just exactly like what you saw for the July 22nd flood. This happens to be from another small watershed, West Branch Herring Run. There were 6 peaks in the summer of 2015 that were more than 1,000 cubic feet per second, 3 that were near 2,000 in 1 2-square-mile watershed. So these are sort of what I consider almost garden variety intense floods. Now then you get the contrasting examples of the Ellicott City floods. And Jim's already reported on this. I'm not going to go into great detail about this, but the bottom line here is that Dead Run got about 5 inches of rain over the entire watershed during that event. That another flood in 2004 produced about the same amount of rainfall in the same amount of time. So here we have the storm total rainfall in the 2018 flood, even bigger, even more extreme flooding. National Weather Service, again, for the second time in 2 years, estimated it exceeded the 1,000-year recurrence interval. This is in Ellicott City, taken from a video camera back behind Main Street. It was a pretty impressive event. There's another video camera looking in the other direction, and you can see that, I'm not going to get into details of it because I don't have time, but we're doing some work to try to reconstruct the flow patterns, and several students working with us right now are working on this. But this shows you different time steps. Flood got pretty close to where the cameras are. So we're trying to see if we can reproduce some of that. That same event produced very high amounts of rainfall in the Maiden's Choice Run watershed. And actually, this is an environmental justice issue. The community near this church, Stillwater Community Fellowship, got between 120 and 130 millimeters of rain in the May 2018 flood. That didn't get nearly as much attention as Ellicott City, and there's still a recovery effort going on. There's actually a lot of work going on to try to understand the social impacts of these on local communities, particularly that are otherwise underserved. Getting back to the Ellicott City discharges, these are some of those values. And without getting into a lot of detail, these include the most extreme peak unit discharge values we've seen for any location in the Mid-Atlantic region. And that includes a lot of historic floods. So where do these fit in the context of other extreme floods in Baltimore and the Mid-Atlantic region? The peak flow rates are unprecedented for any place I've been able to see in the local region for comparable size watershed. What does that mean? They're as rare as what the NOAA precipitation frequency atlas estimates suggest. So we've been working with these envelope curves for a while, and I don't have time to go into this in great detail, but I'll just point out a lot of the big historic floods that have occurred throughout the Mid-Atlantic region and the Central Appalachians plot up against this envelope curve about 1,000 cubic feet per second per square mile, or about 11 cubic meters per second per square kilometer. And that includes things like Hurricane Camille, Tropical Storm Agnes, and a lot of other historic floods. There's the occasional really amazing floods that get up to 2,000 cubic feet per second per square mile. The Ellicott City floods forced me to add a 4,000 cubic feet per second per square mile envelope onto this curve. But they aren't the only ones. This one in Lower Catoctin Creek happened just a couple of weeks earlier and was on that second envelope curve. So we're seeing these things happen that have extraordinarily long recurrence intervals, but they're happening fairly often. In Dead Run, you're looking here at the Dead Run watershed. I'm going to zoom in on one area of it. We have a stream flow record that goes back to 1960. We have actually 6 stream gauges there, but we're going to focus on the Franklintown stream flow record. So this is from an earlier version of the FEMA flood frequency, flood inundation maps, showing you the 100 and 500-year event flood inundation extents on 2 branches of Dead Run on either side of Woodlawn High School. The yellow is the area that was inundated in July of 2004. That was estimated to be a 1 hour rainfall with more than 100-year recurrence interval, and the 2-hour rainfall between 300 and 400 years. 12 years later, we got the same amount of rainfall in the 2016 event. And the flood peak on Dead Run, it was the fourth largest since 1960. So what is either a 100 or a 300-year rainfall turns out not to be anywhere near, it's more like a 20-year flood, which raises the question whether the rainfall estimates are telling us the truth either. So if I just have a few more slides and then I'll be done, but if we look at our annual maximum flood series for a number of our small urban watersheds, to use 1,000 CFS per square mile as sort of a threshold and very intense, there's been 3 since 2012. In a rural watershed, this would be much less common, as I'll show you. That's in West Branch Herring Run. Moore's Run at Radicke Avenue, 6 events since 2003. Dead Run in Franklintown, 3 events since 1972. And one of the tributaries of Dead Run has had 7 events since 2008, close to that threshold. By comparison, Cranberry Branch near Westminster, which is more rural, has had 1 event since 1949 that gets close to that threshold. So that's a contrast between rural and these urban watersheds. But you'll notice these also sort of look like they're maybe going up. So in addition to the studies of time trends, over the entire study domain, we're also comparing watershed average radar rainfall data with stream flow data to see, are there upward trends in the frequency of extreme runoff? Are we seeing comparable trends in forested and less developed watersheds? How do those trends track with the frequency of intense rainfall? It didn't seem to track very well when you looked at the rainfall record over that watershed in North Carolina from the 2009 people by Villarini et al. Are we starting to see evidence that the urban streams are responding to a climate signal? So this is work actually Eli Claggett, who's an undergraduate computer science major, doing some work with us here. What he did was to plot up for us the data that came out of the data sets that Mary Lynn had compiled for, I've just shown you 5 of our local urban watersheds. The black is the stream flow frequency of flow peaks exceeding 1.7 cubic meters per second per square kilometer. And the lighter line is the frequency of rainfall events exceeding 25 millimeters per hour. In every one of these cases, and some of them track better than others, pretty convincing that this is increasing and pretty dramatically over the last 20 years. These are 5-year moving averages to take care of averaging out the year-to-year variations. So that's Mine Bank Run, that's Moore's Run, West Branch Herring Run, White Marsh Run at Fullerton, and Dead Run at Franklintown, which is a little bit different there. So we're seeing what looks like a signal. So I'm just going to conclude by saying the following. Most of our big flood peaks are the product of these short duration events, very efficient in these watersheds to translate those rainfall peaks into stream flow. The intensity matters more than the total accumulation. The hydrograph rises and falls very quickly. The rare events are the ones Jim talked about. Those are the ones that get up above that line on the envelope curve. And we've seen several of those in the area over the last 20 years, 2 of them over Ellicott City in a 2-year period. So they are still rare, but probably not as rare as the reported recurrences. We see those short duration events generating large flood peaks much more often. They are just not rare. And finally, the preliminary results indicate that the frequency of intense precipitation and of extreme runoff does appear to be increasing rapidly over time in our small urban watersheds. And those trends look like they're tracking each other, which suggests that that non-stationary climate signal is now becoming a demonstrable reality in our urban watersheds. I like to say that we can think of these urban watersheds as sort of the canary in the coal mine. They are so responsive to pulse of rainfall that they might be the first ones to actually pick up that climate signal, whereas other watersheds that don't respond as rapidly might not be as heavily affected by a short burst of intense rainfall. So with that, I will stop. These are just some acknowledgements, and I'll just mention, in addition to the Princeton crew, some colleagues at USGS, and then a number of our students here have been working with me on some various aspects of this. So I know we're running a little bit late, but I'm going to conclude at that point. And I think if we have questions, we can take a little time for questions. Anybody want to bite?
I'll ask a question.
Okay.
This question is for Jim, I think. Jim, as I digested what you were saying, it's complicated, but generally speaking, the convergence of the region with the Blue Ridge, the downwind Washington, D.C. corridor, along with Baltimore, and upward or northward wind movement over the Chesapeake Bay are the three factors that, when they converge, can create these very intense rainfall events. And I guess my question is, and then Andy showed a graph of the temperature change of the bay and how its extreme temperatures should be expected to warm. Can we expect the bay to be an enhancer of the frequency of these events as much as the urban heat island? And is that part of the issue that you think you're seeing?
Yeah, I'm not sure it would be an enhancer. It certainly is a big player. And the issue with warming would be how the land water temperature contrast changes with warming. And that's going to dictate the details of the bay breeze. The bay breeze is what plays an important role in creating these convergence zones that are where thunderstorms are going to develop. The urban bay breeze piece is that you get interaction of the urban heat island circulation and the bay breeze circulation, and it dictates this area kind of north of the city, west of the bay, as the spot that is, it's the worst possible spot in terms of being the best possible spot for convergence. Changing the temperature of the city, the bay, or the surrounding non-urban land would move that around. The larger question of whether it would increase magnitudes is, I don't have a good sense for that, but it would certainly move things around.
I'm curious about the effect it would have on humidity as the bay itself warms. And I presume that however much it warms, it's still going to be cooler than the air over Baltimore and Washington.
That's the issue. The air over the bay is cooler, and so it's holding less water than over land much of the time. And so that piece is, again, going to depend on, the relative magnitudes of warming.
Thanks.
Thanks, man.
Any other questions, comments?
Buy a big umbrella?
Good idea.
The water's going to get you one way or the other.
Some knee-high boots.
Hey, Andy, I had a question. Sorry, I'm not, but my video on my computer is also a little messed up, Andy, so I feel your pain.
Yes.
I'm wondering about FEMA and the kind of, when you talk about like 30-year versus 200-year, part of me just starts thinking about the policy implications of all of that, especially for flood insurance programs. And I'm wondering if you could speak to that, especially with the new administration coming in, whether you think there's going to be big shifts in the way that FEMA operates. I'm
not an expert on FEMA. I can say it's complicated. I was actually on the committee of a PhD student in public policy some years ago who actually did his work on the federal flood insurance program. And essentially the federal flood insurance program cannot possibly meet its obligations, certainly not over the long term. So whether or not those map lines are correct, and I think in some cases they're better than what I showed. That was an older version of them. They've probably been updated some, but I tend to think there's a fundamental problem with putting lines on a map and saying that's the line. And actually our colleague, Brian Bledsoe, has done a lot of work on probabilistic flood mapping to indicate that you really can't just draw a line and assume that you fully have captured what's going on. So there's a lot of issues in terms of understanding risk that are quite apart from whether the lines are right that are problematic. FEMA has been given so many jobs to do, and it's almost an impossible job for them to really fully account for this. And for example, they spent a lot of money updating the maps in terms of the quality of the, they paid for a lot of LiDAR to be flown to get very high resolution topography. And then maybe had some updated hydraulic models, but I don't know that those updated hydraulic models have updated hydrology to drive them. So if you don't have the updated hydrology and you don't know fully what's going on with the rainfall, it's hard to know for sure. You know, this mismatch between the rainfall, I don't know that the NOAA Flood Atlas is as far off as what the comparison is with the runoff frequency in Dead Run. I just use that as an example to highlight that there's an issue. FEMA is going to have a problem no matter what, and I think the problem is the current next administration has so many problems that are so expensive, and if they don't control the Senate, they're going to have limited room to move. So I actually don't know the answer to your question, Matt, except that there's a whole bunch of cans of worms hidden inside it. So.
Thanks, Andy. And Jim, I'm sorry if I missed this, but Frederick is kind of expanding rapidly. I was looking at like recent sales of farms around Frederick, just kind of curious to see how fast it'll grow. And it appears that's just going to keep going. Do you think if Frederick were to grow really rapidly and you see an urban heat island kind of intensify out there, that it would really change future projections of what's going to happen in the region, especially given how close it is to the Blue Ridge?
You're muted, Jim.
I don't know if it would be a big signal. I think, you know, Frederick and I-270 corridor are rapidly expanding. And so that, you know, they're a part of the you know, the heterogeneous landscape that defines the region. And so they'll, you know, it's something that will play into, you know, how storms develop over the region. I would doubt that it would be a big change, but it's something that if you were looking to improve predictability, it's one that, you know, you would want to be able to capture that as an important part of model systems.
Cool, thank you.
Okay, we're actually past 1 o'clock. If anybody's got any last questions before we close, I know some people probably have to leave, have had to leave already. But if you have any further questions, please ask them. If not, I want to thank Jim and Mary Lynn, who couldn't be with us, but who's responsible for a lot of this work, for being able to present today, particularly on very short notice. So any last questions before we conclude?
Thank you both. That was fascinating, if not a little bit depressing. But I really enjoyed the detail and the deep dive for considering some of the interactions. And there's a lot of them to contemplate.
Yeah.
Thank you.
Thanks, Matt. All right, I'm going to stop the recording. Let's see. Stop the
I
recording.
do have a quick question for Dr. Miller, if you have one.
Okay, go ahead.
You mentioned how urbanized watersheds might be that first demonstrator of that climate signal.
Yeah.
So I was curious if what you would say the next type of watershed would perhaps confirm or be a secondary demonstrator of that signal as time passes.
Well, I think, I mean, it gets complicated because you have small watersheds are more responsive in general to intensity, right? Because the larger the watershed is more integrating over a larger area. And these intense events tend to be over smaller areas unless you get hit by something like, you know, a big tropical cyclone. So what we typically find, even comparing some of our local watersheds, is that the small urban watersheds, they just respond like that when they get hit by rain. But I can show you some equally small suburban watersheds out even in the Owings Mills area that don't have as much impervious cover, maybe have more stormwater management, and that they don't respond to these short duration thunderstorms. They might rise a little bit, but what it takes for them to flood is a lot of rain over a period of a day, you know, several hours to a day or more. So if we get an increase in total amount of rainfall and it causes more saturation, those places will respond as well. I mean, one of the things we're actually going to do, I showed you the trends for some of our small urban watersheds comparing the rainfall with the runoff. We're going to do that with some of the rural watersheds by the same comparison and see whether, number one, do we see similar trends in the rainfall? Number two, do we see corresponding trends in the runoff or not? So we'll have a better handle on that pretty soon to see whether we're seeing the response. But the example that you saw from Cranberry Branch out by Westminster, oftentimes what you'll see first is that it's the smaller floods that become translated into more frequent, a little bit larger floods. The most extreme ones are rare anyway, but that record didn't show the kind of upward trend as dramatically as what we've seen in these others. But we haven't examined that particular record in great detail yet to compare it with the rainfall. So that'll be an interesting one to look at.
Thank
You want
you.
to add anything to that, Jim?
No, that I think covers it.
Okay, thanks. All right, so if there are no other questions, I will stop the recording now and thank everybody for attending. And remember, I'll be sending out a notice about Dawn Buehler's seminar for December 2nd. So thanks, everybody.
Thanks, Andy.